I really appreciate this opportunity to talk to these bright young minds that you all represent about the new world of AI research. Uh, kind of brings me back, right, to when I was sitting in your shoes. Uh, so today, what I'll do is I'll start by starting with a personal perspective of computer science as a discipline, which has really grown amazingly. I mean, I remember from the time when I went for my undergraduate degree, it was kind of a niche, upcoming field, but a very niche field of engineering, to now pretty much the entire world is being impacted by this field. And in particular, again, a subfield, artificial intelligence within that. So I'll talk about then the dominant paradigms in artificial intelligence, deep learning, and I'll try to explain. I don't expect you to have any kind of a engineering background, computer science. How many of you have done some computer science? Uh, it's surprising, so many of you, but even if you have not done any computer science, hopefully, some aspects you can still appreciate the basic concepts. And then I'll talk about this world of foundation models, which is emerging as the new paradigm, dominant paradigm within the field of deep learning itself, which in turn has become the dominant paradigm for artificial intelligence. Then I'll bring it back to the context of a country like India. What are some of the additional challenges that we see in a country like India to develop AI in a manner that really brings its benefit to billions of people, billions of humans on the planet? And again, no better place than India to look into those kinds of issues, to explore those kinds of issues. So I'll talk about, again, AI as some of our work that we are doing at our research lab, applying AI to languages, health, agriculture. And along the way, I'll talk about many, many challenges, research challenges and takeaways that I believe makes it an, again, amazing time to be a researcher in this field. So let me start with that personal, perspective. I mentioned kind of how the field has grown from this very niche area to pretty much running the entire world. So today we take kind of things like Amazon, Flipkart, and so on, right, for granted. We are able to e-commerce, right, order things from our mobile phone or a desktop, and amazingly kind of things happen. And there's a lot of very interesting, uh, a lot of very non-trivial work, right, that happens along the way before those goods get shipped to you. It sounds very easy, magical, but again, a lot of very interesting engineering work, right, that goes into making all of this go seamlessly. So e-commerce, banking. Today, if you go to a car factory, you'll find very few humans at these car factories. These are all being built by robots. Uh, to even things like there are some parts of the world where self-driving cars are begin to appear on the roads as cabs. Uh, Again, it will be a very interesting challenge to make these self-driving cars work on Indian roads. So perhaps one of you can help make that happen. Uh, Today, but already, right, when we are kind of going from point A to point B, uh, we already use so much of computer science, right? Maps, things like maps, that are not only tell us how to get from point A to point B, they also give us, again, amazingly accurate kind of estimate, right, of how much time it will take us to reach that point, including all those places where we will meet congestion, where we'll hit some congestion. It's, amazingly accurate. And again, how many of you have heard, or let me maybe alternately, how many of you have played with ChatGPT? Yeah, so many hands. Uh, so things like ChatGPT, so I don't need to tell you. Maybe you can tell me what are the interesting things that you found. Any of you want to share some interesting questions you asked ChatGPT and what answers you got? Yeah? Is there a mic?
I personally feel that as an AI model, ChatGPT realizes that it wants to provide more accurate answers. So sometimes I feel it meddles with statistics to give you the answer that you want. Because like research is so vast, you can find some concept and you can find its converse or something that completely disproves that as well. So I think it doesn't always provide you the most accurate of datas, and it tries to focus on what the person might want to get.
That's a very, very insightful answer because most ordinary kind of people, they're just blown away by what they see. Uh, but you're actually kind of going under the covers, realizing that there are so many failure modes that some of these models have. Uh, uh, any other? Any other experiences? Yeah. Can you pass the mic?
Think maths is just very inaccurate. Many times it gives you the answer, but it's inaccurate.
Right. For others, it might be good if you can use the mic, make it.
The coolest thing ChatGPT has is that it is improvising itself. So rather than considering it as a computer system or a machine and trusting it blindly, we must consider it as a human who knows a lot of stuff and tries to improve itself. So like even I encountered some things like I asked it to write some NPM code, but it was completely wrong. It was rubbish. But then it has done many things which are correct. So like we must really appreciate it when we are like talking about it.
Yeah, and actually, one of the things which people noticed recently is many of these large language models have this property of reflection, this emerging property. So if you asked some of these models like ChatGPT, Bard, to critique their own output, sometimes they're able to say, oh, I made a mistake here. And they're able to then learn from that and improve. But the basic point is, I mean, yes, we are seeing all those kind of wrinkles and so on, but the kind of uh, capabilities, right, that these systems are demonstrating is quite mind-boggling, right? So all of this, again, uh, to me, I could have never imagined. When I kind of opted for computer science, I couldn't have imagined, right, that pretty much the entire world. Today, I mean, when you have meetings between prime ministers, presidents, and so on, they're talking about all this. How do we regulate AI? It is the subject, right? The top subject often, right, that even political leaders of the countries are thinking about. So it's been amazing to see, again, how much of an impact computer science has been making on the world. So uh, back to this, yeah. So back to this personal perspective, when I was of your age, um, I'd only heard of computers. Computers were such a niche field. I'd never seen, and I might have seen and not recognized it, but certainly I'd never used a computer before. And by computer, I mean a digital computer. Uh, I mean, computers were known because I remember when I entered my school, nursery, because I used to be very fond of doing these mathematical calculations. So I remember my nursery teacher fondly referring to me as Mr. Computer, but I'd never seen a computer until even after my 12th class, passing out of my 12th class, I'd never seen. Uh, in fact, when I kind of went to IIT Delhi, I had to choose a particular branch. So I just heard that computer science was this very, very exciting area, and it was the branch to pursue. So that's how I ended up, in fact, choosing computer science. Oops, what's uh, in fact, uh, I got my father is a civil engineer, and his closest friends and so on, they were all civil engineers. So in fact, I got some very well-meaning advice from one of my uncles who told me, he said, I would really suggest that you should go for civil engineering, because he said it's a very, very useful field. Of course, they were doing amazing work, and it's a very mature field. He said, you learn those concepts in civil engineering, and you'll be set for life. Whereas if you go for this newfangled thing called computer science, he warned me, you'll have to keep learning all your life. The field will keep changing. So he meant it as a warning, and that turned out to be actually the most enjoyable thing, I would say, about computer science. So to me, I said, well, uncle, what you're saying is true, but I again went by this wisdom of the crowd, right? In Hindi, there's a term for it called bhed chal. So that's how I ended up choosing my discipline, that others who kind of had a choice between various branches of engineering, they chose computer science. So therefore, if I have that choice, let me exercise the same choice. Later, Amazon kind of pioneered this approach. They called it collaborative filtering, right? People who bought these items also expressed an interest, ended up buying these items. Therefore, these items might be of interest to you. So that was this whole field of collaborative filtering to make product recommendations. But in Hindi, there was this very simple term, bhed chal. That's how I ended up choosing computer science. And I would say my uncle was right, that one had to keep learning. But I discovered the joy of continuing to learn. So in fact, I remember and I realized even as we were hiring people and so on, often we look at not just what their capabilities are, how interested, how motivated are they to learn new things, and what's their aptitude for learning, because that often defines success much more than the level of skills that you have at any given point in time, because the field keeps changing. Uh, uh, so in particular, I mean, I cite as a researcher, I talk about, again, some of the work that I ended up doing on optimizing Java programs. And I mentioned that I remember somebody once telling me, oh, I'm not going to hire this person because he doesn't know Java as a programming language. And I said, it doesn't matter. I didn't know Java as a programming language when I graduated because it didn't exist as a programming language. When the language came along, we went and learned it. So as long as people are willing to learn, it should be perfectly fine. There's something that can be improved in the clicker. Okay, maybe I'll just operate on this. Then when I decided to go for a PhD, I would say initially it was very daunting, because what I realized was that in a PhD, in your thesis, you have to show work, you have to do work which is a better way of solving that particular problem than whatever is the best work that has been done previously on that problem. So initially it was very daunting. What if I'm unable to come up with any new ideas? I will end up spending all of this time, right, and never get a PhD thesis done. And going through that process, again, made me realize that even if people are not as smart as me, there's something about the human mind that allows us to come up with new ways. When faced with a problem, we always come up with new ways of tackling those problems. And with enough of hard work, enough of dedication, we are usually able to come up with new, better solutions to these problems. So PhD was a very, very, again, useful experience, because by the end of the PhD, I had more of that confidence that, yes, faced with a new problem, I can hopefully come up with a reasonable solution to that problem. And then joining kind of the various research labs, earlier IBM research, then Xerox research, and then doing my own startup, what I learned in my early days, when I joined IBM TJ Watson Research Center, I was surrounded by kind of some of the world-class experts in the field of compilers. And, and it is from them that I learned kind of, again, striving for excellence. How do you kind of go deep into these problems, understand them at a level that nobody else in the world might understand, and be committed to, again, tackling problems based on your, uh, 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 by developing kind of that depth of knowledge. Uh, and, and it was really after moving to India that I really started appreciating kind of picking the right kind of problems. Because uh, by the time I moved back to India in the year 2006, we were already beginning to see computer science kind of have significant impact on the world around us. And, and, and it was now feasible to pick problems where not only do you advance the underlying field, uh, but by solving those problems, you're able to have significant impact on the world around. Uh, and one thing which I learned, again, largely from my colleagues, is not to be afraid of failures. Uh, because often, even in the world of research, I would see people who would try to play it safe. That let me pick problems that I believe I can solve. Because that way, I'll be able to show some real work. I'll be able to get my whatever paper published and so on. Uh, but that's often not the right way. Instead of picking problems based on what you believe you can solve, picking problems that really matter, where if you were to solve those problems, they will make a significant difference to the world, even if those problems are very, very hard to solve. Uh, it is, it is good to pick problems that matter. And in fact, every once in a while, it's good to pick problems that the world thinks are impossible to solve. Because even if you are unable to solve those problems, by going for these very, very ambitious goals, the kind of learning that happens when you are pursuing these very, very ambitious problems, it's far higher than when you pick problems that are very straightforward. Uh, and, and it pushes you to learn more. And even if you fail at that original problem, often you end up achieving a lot more than if you were just going for very straightforward kind of problems. And if you get lucky once or twice that you solve that problem, you end up getting far higher levels of satisfaction than you get out of just doing some incremental kind of mundane work. Yeah, you have a question or comment? Yeah, so great question. Can you give examples? So we are surrounded by, again, very, very interesting and kind of very, very hard problems. For instance, in computer science, you start with the theory, uh, is P equal to NP? So there are these classes of algorithms that you can solve in polynomial time. Uh, uh, Polynomial function in the on the, let's say, the data sizes. So think of it as algorithms that are polynomial time are those which are normally feasible, that in a reasonable amount of time on a reasonably large problem, you would be able to solve that problem. The computer would be able to solve that problem. Whereas NP, which is potentially problems, let's say, that might take exponential time, uh, you would not be able to feasibly solve those problems. So there are these classes of algorithms. So there are these classes of problems that are known to be polynomial time in complexity. So within theoretical computer science, for instance, there's this class of algorithms that can be solved in polynomial time only with uh, 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 kind of non-determinism. So is this class of algorithms which are in P, is that exactly equivalent to the class of algorithms that can be solved in NP? time. So that's kind of one example. Today, I mean, the world of computers, the world of artificial intelligence is trying to pursue this vision of artificial general intelligence. That's another hard problem. Can you come up with a single, let's say, autonomous agent which is as intelligent as a human being and is able to, again, solve problems in a similar manner as an intelligent human being? So these are examples of different kind of hard to solve problems from the world of computer science. When in the 60s, right, the US President Kennedy, right, laid down that challenge. Can you land a person on the moon and bring them back safely? That was again pursued as this very, very hard, ambitious goal. And often these things are referred to as moonshots and so on. So in any kind of a field, and you look around us, around in the world, you will always find inspiration from many, many hard problems that exist, and where, again, potentially science, potentially technology, right, can make a difference in helping solve those problems. So, so at least my learning was that occasionally it's good to pursue something that the world thinks is impossible. Uh, and if you're able to achieve some of those uh, 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 results, they give you far higher levels of satisfaction than just kind of uh, mundane work. So let me start with kind of, I went and asked Bard. So I wanted to talk about, in the context of this lecture, 1965 is kind of an important year in the history. So I went and asked Bard to tell me some of the important things that happened in the year 1965, and it gave me those answers. In particular for Beatles, one of the answers I was looking for is the song Yesterday. How many of you know about Beatles Yesterday? It is considered one of the most popular songs in the form of, if you look at the number of times a song has been played on radio stations, at least some years back, Yesterday used to rank as the most popular song by that metric, the song that had been played the maximum number of times on radio stations. Beatles came out with that particular album, and in particular that song Yesterday, in the year 1965. So I got some of these answers. Some of them were very US-centric. First spacewalk, but not the answer I was looking for. So I asked, again, ChatGPT as well. And again, it gave me very similar answers: civil rights, movement, Vietnam War, and so on. So any guesses which answer I might have been looking for? What happened? Something important that happened in the year 1965. Any guesses? Yeah. Okay. Perhaps, but yeah, that wasn't the answer that I was looking for. So that happened in the year 1962. 65, there was Indo-Pakistan war that was happening. I was talking specifically from maybe something that was relevant to this lecture. So the first answer I would give you is, I was born that year. But again, I mean, I don't expect ChatGPT or Bard to give that answer, because my being born or not born doesn't really matter to the world. It matters to me, but not to the world. The answer I was looking for was Moore's law. How many of you have heard of this term, Moore's law? Oh, wow, I'm surprised, many of you. How many of you have heard of Newton's laws of motion? I'm expecting every hand to anybody who's kind of awake, right? Should be raising their hands. So unlike Newton's laws of motion, Moore's law is not a real law. Newton's laws of motion you can actually kind of bank on and so on. Moore's law was actually a prediction made by this person, Gordon Moore. In fact, Gordon Moore passed away only recently, earlier this year, a few months ago. Uh, he went on to be a co-founder later of Intel Corporation. He was a co-founder of Fairchild Semiconductors. Uh, he had written this paper in the year 1965 that is now known as Moore's law, as having proposed Moore's law. In that paper, he had predicted that you would be able to, with every new generation of integrated circuits, you should be able to roughly double the number of transistors you can put on a given microchip, roughly at the same cost. So this is what he proposed in the year 1965. And it was actually a prediction, but it was a very, very bold prediction. Again, I mean, another example of boldness, that he made that very bold prediction, and the entire semiconductor industry, the entire world, started working very hard towards making it come true. In fact, this became a defining principle because every company, Intel, Motorola, IBM, they were all kind of assuming that their competitors were going to double the number of transistors in the next generation. So they worked extremely hard in order to stay competitive, to make sure they keep doing the same thing. So this, in my view, is one of the very defining moments in computing history, which has really led to the whole field of computer science, right, becoming so dominant, so important, right, to the entire world from this niche field. This exponential, because what happened with this doubling of the number of transistors on the microchip, roughly what it meant was that you could double the amount of compute power. For roughly the same cost, you could double the amount of compute power that you had available at your disposal. And exponentiation is a very, very powerful phenomenon, which mostly we humans do not understand the power of exponentiation very well. How many of you can, from this picture, how many of you can relate a story that you might have heard in school? I don't know if they still teach those stories in school. At my school, we were always taught this particular story. So I see a few hands. Can you narrate the story? Is there a latency?
Yeah.
Yeah.
The story was actually narrated in one of the previous talks as well.
Okay.
So basically, some minister in a court, I'm assuming, did something great, and when he was asked what prize he wanted, he said that all he wanted was a grain of rice for the first square on on a chessboard, and a 2 to the power of 1, 2 to the power of 0 in the first one, 2 to the power of 1 in the second one, 2 to the power of 2 in the third one, and so on and so forth. And it seemed like a little prize to the king at first, but then at the end it was 2 to the power of 64 grains that he had to give, which is a humongous number.
Yeah, so thanks for narrating the story. So again, as you mentioned, I think maybe one of your speakers has already used that story in their lecture. So the point of this, which maybe the previous speaker already said, was that initially, right, the king thought this was a very small kind of a prize that this person was looking for. So we don't understand this power of exponentiation. It was only when you got to the middle of the chessboard that the king realized he would not be able to honor the promise. So what I'm arguing is a very similar thing has been happening with the field of computing, fueled by Moore's law, right? So Moore's law, Moore in the year 1965 predicted that every chip you will be able to double the number of transistors. So initially, all these chips, they don't look very powerful, but as you start getting to this part, they start to become extremely, extremely powerful. And now their power kind of goes beyond what you had imagined. So, and in fact, this analogy with rice grains and computing is very apt. I remember a factoid when I moved back to India in 2006. I used to give all these talks on behalf of IBM to customers. And one of the factoids that was shared with me was that in that year 2006, it said we are producing more transistors this year as humanity than grains of rice. So in 2006, I felt we had reached this point analogous to the second half of the chessboard, just like the king realized at this point that he would not be able to honor the promise. Uh, there was too much of rice that he had to give away. By the year 2006, when we as humans were producing more transistors than grains of rice, I would say we had reached the analogous point here that now computing had become so powerful. We had so much of powerful computing at our disposal that things that were previously thought of as science fiction were now possible. And, and, and we have continued with now those exponential advances. And we are now maybe somewhere here, and Moore's law has slowed down. I mean, you no longer see those dramatic doubling, but you continue to have still that growth in computing power. In fact, much of this field of artificial intelligence, deep learning, it is riding on continuing kind of exponential growth in the amount of compute power which is being applied towards these problems that, again, we are reaching kind of points beyond human imagination. And this is what is really fueling this whole revolution of computing, and in particular, the field of artificial intelligence and deep learning. So deep learning is nothing but, so how many of you have heard of the term deep learning? You see many hands. How many of you know how deep learning works? I see a few hands. So those of you who already kind of know how deep learning works, please bear with me and correct me if I make a mistake. But for those of you who have heard the term deep learning but don't know how it works, I'll try to explain how it really works. Because it's been nothing short of kind of almost like again, a miracle. And again, there are some very, very interesting, even life lessons from the pioneers of deep learning. So deep learning, so a few years ago, the pioneers of the field of deep learning, Jeff Hinton, Jan LeCun, and who's the third guy? Bengio, Yoshua Bengio. Sammy Bengio was his brother at Google Research. Yoshua Bengio. These three people who were pioneers of this field of deep learning, they received the Turing Award, which is the highest award given in computer science, the equivalent of Nobel Prize, for their contributions. And a lot of their work for which they were given this Turing Award, a lot of their work was done in the late 80s. And in fact, for close to 20 years, this artificial neural networks, the area in which these people were working, was considered a bad word because the entire world knew that this artificial neural networks just don't work. And many of these researchers like Jeff Hinton and so on, their papers were getting rejected, they were ridiculed. Why are you continuing to beat this dead horse? Why are you continuing to work on this in this field of artificial neural networks when we all know they just don't work? They persisted. And again, it was really the power of computing that led to the revival of this particular field. So these artificial neural networks are not, so they are loosely inspired by how the human brain works. And within the human brain, right, you know there are neurons that fire, there are these synapses and so on. So don't go too much by how the human brain works. The analog, the inspiration for neurons in these artificial neural networks, these neurons are very simple mathematical units which are doing an extremely simple mathematical computation, which could be as simple as taking an input, multiplying it by a weight, adding another offset, and passing on that output to the next layer. Or it could be something like taking these input values, taking the maximum value, and then passing it on. Or looking at the input, if it is above a certain threshold, then say this is 1. If it is below a certain threshold, then it's 0. So computations as simple as that are done by these individual neurons, but when you organize them in the form of multiple neurons in a given layer, and you have multiple layers of these doing a computation, and what do I mean by computation? Let's say you feed it the image of a cat. And by feeding it the image of a cat, it means you're feeding all those pixel values, right? The image would be represented through these pixels. So you feed those pixel values and you kind of have this neuron act on that pixel value, multiply that by that pixel value by a weight, add an offset, pass on the result, and so on. So when you do all these simple computations, the neural network is able to come out with the answer that this is the image of a cat. I'll explain shortly how these neural networks are able to do that. To do them, you have to train these networks. And by training the networks means you have to come up with, again, the values of all those parameters that these different neurons control. I mentioned that this neuron might be simply taking the input, multiplying by a weight, and adding an offset. What should be the value of that weight? What should be the value of that offset? So those are the parameter values that need to be determined. And coming up with all those parameter values, that is referred to within this network, that is referred to as training the network. So this is how and I'll shortly explain how this neural network gets trained, but these neural networks, they could be trained to now give it, answer this. And in particular, this field of neural networks made a comeback through this particular challenge. There was this ImageNet challenge. There was an annual competition that used to be organized where you had to write an algorithm that would, given a set of images, that algorithm had to tell you what was the type of that image. So there were 1,000 classes based on the dominant objects, that this is an image of a leopard, this is an image of a cat, this is an image of a mushroom, and so on. So there were 1,000 such classes, different object categories, and you had to, given an image, a new image, you had to say which category this image belonged to. And this used to be like an annual contest, and often you used to see a few percent improvements in the errors that were made by these algorithms. So in the year 2010, these algorithms were misclassifying almost 30% of the images. That was the kind of best known algorithm, that was the error rate. And next year there was a minor improvement, but then in the year 2012, suddenly there was a very unheard of, very dramatic jump in the accuracy of the algorithm, almost at close to a 10% jump in the accuracy. And that algorithm this year was based on the deep learning methodology. And in fact, in subsequent years, it was really deep learning based algorithm that really took over as the best method for solving this problem. And in fact, compared to 26% errors, right, in the best performing algorithm, humans were at the level of making about 5% errors. So even humans wouldn't get everything right. And in the year 2016, these deep learning based methods surpassed the ability of humans at that particular narrow class of problems, ImageNet challenge. So this became kind of, this particular result in 2012, this became a defining moment that led to the comeback of deep learning. So artificial neural networks, again, it was Jeff Hinton and his students who had developed this particular approach. And very soon after that, not just in problems like image classification, in a lot of classical problems like speech to text, also known as automatic speech recognition, given this audio signal, can you say what are the words that are being said in that audio signal? That this is saying, how cold is it outside? Speech to text, this was a very well-studied problem. I mean, researchers had been working for decades, building these language models, acoustic models, and so on. All these different machine learning-based methods, and out came deep learning, the same kind of deep neural network where you didn't need to train it specially for a given language. All you did was you gave this deep learning many examples, labeled examples of audio signal and what actually were the words being said in that. So by giving that network many labeled examples meaning audio signal as well as the actual speech, the text that was said in that audio signal. By giving it all these examples, very soon deep learning based methods became the best methods at solving this text to speech. Likewise, machine translation, taking this text in English, translating that into French. Again, there was a whole research community that used to work on various techniques like first rule-based methods and then statistical methods for machine translation. Deep learning became de facto the dominant approach to solving this problem. And then a variant of this first problem where given an image, you're not just saying this is an image of a train, you're coming up with the description of that image, just like a human would, and coming up with that description automatically, coming up with that option automatically. That was given as one of the tasks. And now some of you may recognize that even the reverse is possible. Today you have AI models that given a text prompt will actually generate an image like this. So even that has become, I'll come back to that generative AI trend. So all of these, what was remarkable was that they were all kind of different research problems with their own research communities, experts in those fields. And within a few years of this deep learning approach being demonstrated on the image classification problem as the best way of solving that problem, within a few years, deep learning became the de facto standard, the de facto best method of solving all of these different problems. So which is why it's worthwhile understanding how these deep learning networks really work. How do you train these networks? So essentially what you do is the initial approaches to training these neural networks were based on what is known as supervised learning. Supervised learning means that you start with a lot of data points, and for each data point, you have a label that tells you what the right answer is for that data point. So let's say you're wanting to solve the problem of image classification. You feed it millions of images, and for each of those images, you have a label which is telling you what is that image. Is this image of a cat or a dog or a human, of a car, and so on. And the way you train this network is through essentially optimizing. First, you formulate something called a loss function. A loss function is actually nothing but some mathematical function that represents the difference between the predicted output of the neural network and the correct output. So let's say the correct output is let's say you want to build a neural network to predict the height of a person. Given an image, tell me what's the height of this person. So you feed it all these images with the actual height of the person. You ask the network neural network, given those data points, it'll do all those computations, right, and come up with some prediction. You take the difference between that prediction and the actual value, the true value, and typically the way you formulate a loss function, right, in many of these, you take the difference, you take the square of that difference, and then you sum the squares over all these values, and you say minimize the sum of squares, right? And you can intuitively understand that by minimizing the sum of squares, you are trying to make the loss function become very, very small, right? The difference between predicted value and the actual value, you want it to become very small. So it's all about minimizing, first formulating the loss function in terms of given a data point, given those model parameters, these are the weights in that neural network that I was mentioning. So you will multiply many of these data points with, again, some of these values of these weights and so on. You'll add some other parameters and come out with this predicted value, and the difference of that and the true label, often summing up the squares and so on, right? That's the loss function. So to minimize the loss function, so typically in mathematics, so you've all been studying kind of mathematics. When you want to come up with optimizing a function, how do you solve that problem? There's a given function, and you have to say, compute the value at which it has the maximum or the minimum value. Differential equations, exactly. So what you do is you solve it using differential calculus. So given a function, you know that if you take the first derivative of that function with respect to x, you know that at the extreme point, whether it's minimum or maximum, that derivative is going to be 0. So you try to solve for that value of x when this derivative is 0. So you do a very, and again, this is possible sometimes analytically when you have simple functions like this. Sometimes you don't have simple functions. Sometimes there isn't just a unique minimum value or a maximum value, right? There are many such points. And there are these functions known as convex function, right? Where any local extreme point, any local minimum is always going to be the global minimum. But then there are functions like this, which are not convex, where you can have multiple minima points, and a given local minima that need not be the global, local minimum need not be the global minimum point. So in neural networks, you typically have to go for this non-convex optimization. So you formulate that loss function in terms of those model parameters and as a function of the data, and then you have to take the derivative with respect to that data and solve for that being 0. So when you don't have closed form functions, right, something like this function, the way you solve it is you look at the gradient of this function at a given point right? Let's say you are at a given point x. You look at the derivative of this function. You look at the gradient, and what you do is you say that if the derivative, if the gradient is positive, then you want to make x smaller if you want to move towards kind of the minimum point. If the derivative is negative, then you make x larger. So this has motivated this algorithm called gradient descent algorithm, which is used to come up with the weights, the values of those parameters of a neural network. So given a loss function, and you can see that with the help of this example, that let's say if this was a function and you were trying to find the value of x at which this function has the minimum value, you can look at the gradient at different points in x, and if the gradient is negative, you make x bigger. So here, right now you are at this point, so gradient is negative, you make x bigger, you go to this point, again you look at the gradient, it is negative, you make x bigger again, keep doing that, and then you go to this point and you see the gradient is positive. So now you need to make x smaller. So through this, you already know that yes, somewhere between those 2 points would lie the minimum value. And one of the things that as you get more sophisticated, initially when the gradient is large, you can move x by a bigger value. And as you start getting closer to your destination, you start moving in smaller steps. So essentially, this is the idea that gets used in the training of these neural networks. And all of this large amount of compute power is now helping the training of these networks, even large networks, computationally feasible, because now you can kind of feed those networks. So it was only as you started feeding these networks millions of data points, and again these determined based on those millions of examples. So this is how all these neural networks got trained with often very, very large data sets, typically numbering in at least millions. And then likewise, training these neural networks where even the number of parameters were getting into initially thousands and later millions. And in fact, there is a mathematical result. There is a theorem that says that with a 2-layer network, with just one intermediate layer, you can actually approximate any computable function. If there's any mathematical function, it can be approximated by even a 2-layer neural network. So there is a sound kind of theory underlying all of this artificial neural networks, which has now been applied towards tackling many of these problems. So any guesses on or do you know how many parameters some of these models like GPT and BARD and so on, what they have? So you're saying GPT-4 has? Yeah, it has. So many of these models now have hundreds of billions of parameters. So number of parameters is not always now announced. Google, for instance, announced this model called PaLM last year, which had 540 billion parameters. So 540 billion values were being determined, had to be computed to train that particular network. So these kinds of networks require huge amounts of compute power, and it's again in accordance with Moore's law that growing amount of computational power has now made these kinds of computations being done using neural networks now feasible. But one major drawback of all of this was that you needed lots and lots of labeled data. So to train a network on all these images, you needed to come up with millions of images where some human needed to analyze that image and say what that image is all about, and which is not always feasible, right? So if you are, let's say, for instance, Dr. Anurag Agarwal, right? He does a lot of work on applying AI for healthcare. Now, if you wanted to make a health decision based on patient data, to train his algorithms, right, in this conventional way, he would need labeled data for millions of patients. So for millions of patients, he would need that data point plus expert opinion, expert doctor's opinion on, let's say you were trying to see, let's say you were trying to look at X-ray images of lungs, and you had to say, is this a case of a lung cancer or not? You would need, again, millions of these X-ray images of patients with annotation about, is this a case of malignancy or not, and then feed those data points to a neural network, right, to train such network. So yes, it works, but it has that drawback that you need lots and lots of labeled data, not just lots and lots of computation. So compute power is becoming kind of fairly freely available, but this lots of labeled data often is not so easy to come by. So that became a major bottleneck, and that has motivated this new approach called foundation models. So all of these ChatGPT, BARD, and so on, right, that you might have heard about, all these models, DALI and so on, these are all examples of foundation models. So just like deep learning kind of was just a narrow field within the overall field of machine learning, which was just a narrow field within the overall field of artificial intelligence, but just like deep learning started becoming the dominant approach to artificial intelligence, likewise, these foundation models are now becoming the dominant method within deep learning. And to explain how foundation models work, let me again explain it very simple ways. So the precursor to all of these foundation models was a model called BERT that was built by Google researchers in 2018. And to explain how BERT works, what they did was they took a lot of the text that was freely available on the web from sources like Wikipedia or digital books. And that model was trained using a methodology that reminds me of this exercise that at least my English teacher used to give us when I was, again, in school, primary school. So how many of you were given this exercise, fill in the blanks, by your English teacher? Is it still used in teaching English? I think, again, all of the hands. So when the teacher was giving you this fill in the blanks exercise, what were they testing through this fill in the blanks exercise? What were they testing? Ability to guess the word. And what did you need to be able to guess the word correctly? Knowledge. So, yeah? Vocabulary. So you needed to understand English as a language in order to be able to guess the word. So that is one. What else did you need? Intelligence. So, or some understanding of the context, from the context, right? Fill in the blanks means from the rest of the context, you need to now tell me what that missing word is, right? So you have to you characterize it as intelligence, you can think of it as whatever, reasoning, some understanding of the world, that from the rest of the sentence description, you're coming up with some way to do that prediction. So a very similar exercise was given by these Google researchers to this model called BERT. So you can think of those Google researchers as those English teachers, and that model, this neural network, as that poor student who's asked to fill in the blanks. So BERT was the student who was asked by the teacher. So the teacher fed it lots and lots of text, Wikipedia text, digital books, stuff that shows up in web pages. And remember, the way previous generation of deep learning algorithms were trained, you were always kind of coming up with human annotations. You were feeding it data. You were also annotating the data with what that answer is. Now, the beauty of this approach was there was no annotation needed, because all you did was you masked a few words. You started hiding a few words. So roughly 15% of the words were hidden from this model. So fill in the blanks. That's why I'm referring to this as a fill in the blanks exercise. And the model was asked to predict those words. So in that sense, it's a case of supervised learning where you already know what the missing word is because you hit that word. So without any human having to annotate, you already know what those labels are. You just hit those labels from the model. So just like while doing this fill in the blanks, for you as a student to be able to fill in the blanks correctly, you needed understanding of English, you needed some understanding of the world, some ability to reason about the world, and then you were able to answer. Likewise, now Bert, in order to come up with correctly predicting those words, Bert now needs to A, have an understanding of English as a language, and it needs to have some ability to reason about the world. It needs to come up with some representations of the world in order to be able to correctly predict those. And technically, what was an approach to being able to predict those words? There was another critical particular innovation called the transformer architecture. How many of you have heard of the word transformer architecture? So I see a few hands, doesn't matter. I'll explain it very simply. In order to predict this word born, Obama was dash in 1961. What transformer architecture does is it says that, look, for me to be able to predict this word, I am going to pay attention to words in a certain window. I'm going to look at words both preceding this blank as well as following this blank. So there are also some models which only look at what precedes. So when you're typing these days, right, on your mobile or on Gmail, the system already predicts what you're typing. Those models only use what is before the blank, because before you wrote something, it only looks at what you've already written. So those are based on something called LSTM, which just looks at kind of the words preceding, but BERT would have the luxury of looking in both directions. So in fact, the B in BERT stands for bidirectional. So you look at words in both directions in a certain window, and you pay attention to them. And you have to pay higher attention to certain words. Like in this case, the words Obama, 1961, Honolulu, Hawaii. These are going to be much more important to helping this model come up with the answer born. And essentially, this particular, so in a very, very high level manner, there was a particular way of building these neural networks that was referred to as the transformer architecture. So in fact, that paper on transformer architectures, it came out in the year 2017. It was a paper called Attention is All You Need, a pun from All You Need Is Love by Beatles. Attention is all you need. It's become one of the most famous papers in the whole discipline of artificial intelligence, because all these neural networks were built using that approach. And the other beauty of this approach was self-supervision. So in supervised machine learning, you are feeding it labeled data. In self-supervision, you have the data itself provide the supervision. Like here, the data was already there. By hiding a few words and asking the model to predict those, you kind of gave it a supervised learning kind of a setup. So this became kind of BERT when trained in the year 2018, it became kind of the best way of solving many, many different kinds of language modeling problems. So there were a lot of neural networks that used to be built for different kind of natural language processing problems. What are examples of some of those problems? One is sentiment analysis. Why do you need to do sentiment analysis? What is sentiment analysis? Any of you have? Yeah. Emotion, yes. It could be the emotion of a person, it could be the emotion of a social media post. So why is sentiment analysis important? Because often, let's say I'm running a company, IBM. I want to monitor what are people saying on social media, on Twitter. Or if I'm Prime Minister Modi, I'm interested in what are people saying about me on social media? Are they generally having a positive opinion of me, or are they having a negative opinion of me? So that's sentiment analysis. There are other NLP problems, natural language processing problems, like question answering. Given a piece of text, can you answer, right? You're all given all these exams where you have to kind of, based on what you learned, you have to now answer questions based on, let's say, give a material from a textbook, right, that you learned. Often now these kind of problems are given to these deep learning based methods, right? So what BERT showed was that for a variety of different kinds of natural language processing tasks, whether it was sentiment analysis, whether it was question answering, or whether it was another task could be summarizing. So given a large piece of text, come up with a nice summary of that text. That's another natural language processing task. So a BERT-based model started doing better at all of these different tasks than individually trained deep learning methods. So this was again analogous to how deep learning started becoming the best way to tackle many of these different kinds of problems: image classification, speech recognition, language translation, and so on. For a lot of different language modeling tasks, this approach, based on pre-trained models, using self-supervision, often using the transformer architecture, this became the best way to tackle these problems. And this phenomenon, this way of tackling these problems, has been called foundation model. BERT is the first kind of recognized as the first example of such a foundation model, that they provide excellent foundation for solving a problem. And GPT-3, GPT 3.5, GPT-4, these are all examples of a foundation model that now a single model, GPT-4, is so powerful that a chat interface, if you provide on top of that, it is able to carry out a conversation with you almost like a human would. Of course, I see all those skeptical faces. Yes, there are gaps, but the kind of capabilities, right, that these AI models are able to already achieve is quite impressive. So at Google Research, my colleagues built this model called PaLM 540B, and this was named 540B because it had 540 billion parameters. And when, after building that model, they tried it out on 58 different problems. So there was a set of benchmarks prepared where 58 different problems, things like sentiment analysis, summarizing, question answering, and so on, these are all posed as different problems. And on that set of 58 problems, a single model, this PaLM-based model, started doing better than the previous state-of-the-art, previous best approach on fairly large percentage. So I don't remember what this exact number is, of the order of 40 tasks, more than 40 tasks. Just the single model PaLM is doing better than the previously specialized trained models on those tasks. So these models are now pretty impressive, which is why, again, you are beginning to see these models approaching, right, those levels of, which is why it is giving hope that in the future we can get to a single model that will be able to have a level of intelligence comparable with a human being at a variety of different kinds of tasks. Just a single model we should be able to train. So One of the very interesting thing about these large language models is that while you know that as you start building larger and larger models, you know for sure that they will have new capabilities, more powerful capabilities. Uh, there is this phenomenon called emergent properties. Uh, some new properties emerge as you start building these models, which you didn't even, which you couldn't foresee. Even people who were building these models couldn't foresee. So when Palm was built, one of the emergent properties that researchers discovered after they built Palm was this chain of thought prompting. That if you give this Palm model this puzzle that Roger has 5 tennis balls, he 5 more cans of tennis balls, each can has 3 tennis balls, how many tennis balls does he have now? And likewise, this cafeteria had so many apples and so on. If you ask it to give the output, often it would give wrong output. Just like you mentioned, right? ChatGPT, Bard, they will often give wrong results. But if you ask this model, please explain your output. So this is again similar to many times, right? Our math teachers would say, don't just solve the math problem. Show me step by step your way of working, right? Because otherwise you could have just guessed it, or you could have just copied the answer from somebody. So the teacher wants to see step by step, how have you solved the problem? And the benefit of that is that even if your final answer is incorrect, the teacher would say, I'll give you partial credit, right, for showing at least the right steps, the right way of solving this problem. It turns out that when you ask these models to show their thinking step by step, their actual ability to give the correct answer improves. So another emergent property that people have seen with things like GPT-4 and so on is this self-reflection, that you ask the model a question, it gives an answer, and you ask the model to critique its own answer, to reflect on it and say, do you think your answer is correct? And often this model is able to now kind of find flaws in their previous answers. And then they're able to correct their mistakes. So that's the property of reflection that seems to be emerging in some of these models. So this is again a very interesting phenomenon, and it is not just limited to language models, even on images. So I was mentioning, let's say, if Dr. Anurag Agarwal wanted to come up with a model to come up with, given X-rays, tell me, is this a case of lung cancer or not? Or given a set of images, tell me what skin disease this person has. Instead of the traditional way of building these models would be to feed them lots of images with labeled data, lots of these skin images or X-ray images with expert opinion on what the actual disease is. And then the model, given all those data points, it starts getting trained. Now, instead of all these labeled images, if you start feeding these models lots of unlabeled medical images, and again, you can play those tricks of self-supervision. You can hide a certain part of the image and ask the model to predict what that missing part is. Or so that is known as masked encoding. There are also other ways in which people use self-supervision on images, which is known as contrastive learning, where you say, if there are two parts of the image, you come up with representations of those images, and if they come from the same image, those representations should be very close to each other. If they come from different kinds of images, they should be very far from each other. So this way, what researchers have seen is that if you start with unlabeled medical images and you do self-supervision on those, and then you do what is known as fine-tuning of that model with some labeled examples, you're able to get better results than or often better results with a few thousand examples, you may get more accurate models than models that required millions of those images. And we are seeing similar things with things like speech to text. So Google recently released this model called Universal Speech Model, a single model that can understand over 300 languages of the world. So you no longer need to build a separate model for English, one for Hindi, one for Tamil, and so on. You can build a single model that understands all of these languages, and instead of having to feed it with, traditionally you had to feed it tens of thousands of hours of speech data, which was also labeled, speech data along with the words, what was said. Now, with only of the order of 1,000 hours of labeled speech data, and by feeding it again all these millions of hours of even unlabeled speech data, these models are performing as well as models that might have been trained with, let's say, 50,000 or 100,000 hours of speech data. So this is becoming a very, very interesting kind of a phenomenon. And these models are also becoming multilingual, multimodal in nature. So ChatGPT and so on, the initial versions are all based on text, language. But already ChatGPT has announced, right, that you can now also feed images. Very soon, you'll start to see sound, video, and so on. So Google has already announced this effort called Gemini, which is again a single model which is able to process images, text, sound, video, and so on. And these models are able to answer kind of complex questions. Like, for example, you feed it this video. In this video, this is like a cooking video. And you can feed an AI model this particular video and ask it the question, what is the second ingredient which is poured into the bowl? And this AI model is able to answer this question. So already you are beginning to see AI models with this kind of level of capabilities. And another very surprising advance has been of these generative models in creativity. So today, in fact, there's this researcher who refers to Fredo Durand, who refers to this AI-based image synthesis as the biggest innovation in image making since the invention of photography 200 years ago. That today, you feed this model a simple text prompt like night is long and full of terror, and it generates this scary looking image. Now this image, you might say, it has picked up this image that existed on the web, which maybe had this caption, so it has just kind of done the match, and that's how it has generated. But let me give you this example. This is a very, very contrived prompt, abstract surreal painting of a melting white Porsche oozing onto a chessboard. Chess pieces are scattered all around. A melting golden clock shines brightly in the background, soft and airy lighting. Now this is a very, very contrived kind of a text prompt, right? Nobody in their right mind would be imagining such a picture. And you can see that this text to image model has generated an image which is very faithfully conforming to this prompt. So these models are made possible by what is known as diffusion models. And again, the ideas behind diffusion models actually comes from the study of the field of thermodynamics. So in thermodynamics, you have this notion of entropy, which always kind of keeps increasing. There's a similar notion of entropy that they have, that you first get into a destructive process, which takes this data, converts it into noise, and then you have a model that tries to map that noise back to data. And this particular model, so again, this was pioneered by this guy Jasha sold Dick Stein at Google Research, inspired by ideas from thermodynamics, and 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 you have these models like Imagen model, where you start with this text to image diffusion model first at a kind of a low resolution, and then you have further diffusion models that increasingly refine those resolution. And what you're seeing is again that phenomenon of emergent properties. As you start building larger and larger models, they become more and more powerful. So for that same kind of basic way of solving the problem, the same neural network architecture, when you trained it of the size 350 million parameters, and you fed it this prompt, a portrait photo of a kangaroo wearing this orange hoodie, it generated this picture. I mean, yeah, it has that orange, some dress, it has those sunglasses and so on, but it's not quite really talking, I mean, this is not really the Sydney Opera House, doesn't really look like, this doesn't look so much like a kangaroo. But as you start making these models bigger and bigger, you look at this, output of a 20 billion parameter model, and you see the quality of this and the faithfulness with which it is kind of observing the prompt. So these are examples of, as you start training these larger and larger models, there are these emergent properties which are bringing them, again, really, really high quality. And this is again led to, again, further work that given a dog, you might want to see the dog. Can you generate image of that same dog in different backgrounds? So it is being used for personalization. You can generate entire videos. So today, to generate a high quality video, it still needs to be short, but very soon you'll start to see even longer videos. Give it this prompt, a glass bead falling into water with a huge splash, sunset at the background, it is able to generate this video all automatically. Also things like, given this image, so normally you would have this cropping functionality, right? Often that there are tools that give you a cropping functionality. Given this image, can you crop it? Cut out these ends and just show what is in the middle. But if you are just shown this image, can you uncrop it? Can you imagine what might be surrounding this part in the image? And it generates an image like this, right? And you can see this is both very high quality, quite believable, very, very realistic. So these kinds of applications are propping up in, for instance, helping create ads, helping create marketing material. A lot of companies are beginning to do that. But still you have some many outstanding issues with many of these. Things like safety. So one of the known, in fact, drawbacks of many of these models, one of the known problems of many of these models, which some of you already observed with ChatGPT, is that these models can give out wrong answers, and wrong answers in a very convincing manner. So it becomes unlike a human, because what happens is, human, if you ask me a question and I have no idea, I may pretend that I know the answer, but deep inside I always know that I don't know. These deep learning systems, even deep inside, often they don't know that they don't know. So they will give out those wrong answers very, very confidently. Because if you also ask the deep learning model, don't just give me the answer, also tell me what's your confidence in those answers. These models will often give out those wrong answers with a lot of confidence. So which can create safety problems. I mean, if you're relying on something to help you with medical diagnosis, and it very safely gives you a completely wrong diagnosis, that can create a major safety issue if the doctor is relying on the output of that model, right, to do the diagnosis. There are issues of bias and fairness. It has been seen that some of these image processing AI models, they work very well for images of, let's say, white men and women. You feed it the image of a black person, and it will start saying, oh, that's a chimpanzee, or that's a gorilla, which is very demeaning to the person. Or things like all these language models. So today you have a lot of these AI companies which are saying, oh, we'll analyze your resumes and automatically help you identify the right candidate to shortlist. Now it is known that when humans look at resumes, a lot of studies have shown that women have a disadvantage when it comes to high-tech jobs. If you were to apply and if you were to send your resume, if the only thing you changed was your name from your true name to a male-sounding name, the sad reality today is that your chances of getting shortlisted and so on go up. Because of the bias that often we humans carry, right, when we are making these decisions. Now, if you train an AI algorithm based on all of this labeled data, guess what? These AI models start exhibiting some of those same biases that we humans carry. So understanding all of those bias issues and fairness issues is again a huge problem. Yes?
Sir, adding to you, so from 2013 to 2018, Amazon had like some sort of this model only. I guess 57,000 female employees were rejected just because of this reason. And the ratio of female employees to male employees in Amazon raised up to 82 to 82, like 82, 18%. So that is something like, sir, how do you think we can deal with human biases in AI?
Yeah, so I think one of the things we need to do is we humans need to start becoming more aware of our biases and in fact start committing to, again, both developing that awareness and then addressing those biases, confronting those biases within ourselves and commit to making better decisions, right, which are fairer. Uh, the problem is that many of these machine learning with humans, at least you can say that, look, I'm going to take all of those humans through a certain training where we are going to make them aware of all of these biases that we humans carry and so on. What happens is that if these models have inherent biases, coupled with this problem of explainability, right? Because the way these deep learning models are operating is they have billions of parameters. Now, which set of parameters are encoding those biases is very hard to see. Nobody, no human has any clue in terms of how these neural networks, I mean, we understand them at the level of, oh, loss function has been optimized through derivative with respect to the model weights, and therefore we have chosen model weights that will lead to the minimization of the loss function, and therefore as few departures, right, from true predictions. But how do those individual model weights, values, encode kind of how you are making those decisions? That's not very explainable. So that combined with, if you are learning from humans and encode some of those same biases, basically it makes it then very, very hard to be able to debias a neural network. So it's a huge challenge. Yeah, so you're asking the question, so these are all interesting approaches. So in fact, one of the ways in which another problem of safety is that some of these AI models, right, could be used to give you answers that cause you to do harm to others. So already many of these models, the way they are trained to not provide those harmful responses is there is another instance of an AI model which is watching what this one model is doing. So what you just asked exactly is being done to try and make these models less harmful. But all of this is a very, very active area of research. We still do not, I would say that all of these are fundamentally unsolved problems. So these are great problems for you if you were to pursue a research career, attack some of these research problems. Yes.
Hi, sir. So my question was that let's say if we have any question to ask any AI model like ChatGPT or Bard that's not available word to word on the internet. Like let's say I have a question that was provided in one of the math tests provided to us at LGP. If it's related to something in maths and science, it would be able to use concepts that it already knows, like BPT or similarity of triangles, to kind of solve the question. It may not be 100% accurate, but it does have an accuracy rate. But if we talk about questions in the field of like history or economics, I don't think it's able to string concepts together that well. Like let's take the Pasha's Sorrow. It's a painting by the French classic artist John Lone Jerome, and I asked both Bard and ChatGPT about the symbolism behind the painting. Bard was honest that it did not know much about the painting, so it was making guesses. But like I feel a 15-year-old could have made better guesses if they've studied in CBSE. And as for ChatGPT, it created some other like completely different painting and tried to convince me that the author had made that painting instead of the one I asked for. So like, why is it that these AI models aren't able to connect concepts that well in fields other than science and maths? And I'm not sure how busy you guys are at Google Research right now, but like, if you have any free people around, can you ask them to start working on this?
So thanks for that. So thanks for that criticism and very, very, very good input. Perhaps it's reflective of the kind of data sets, right, that these models have been trained on, that that the kind of data that they've been exposed to doesn't reflect that richness of art and so on. So yeah, thanks for that great input. Yeah.
So I had one final question because
Yeah.
this has been something I've always had a doubt of. So, because with the increasing computer performance, there was an AI boom in the 2000s. But today, is there a strong link between improving the hardware capabilities and what we can, like, and advancing AI? Because the Moore's law does not actually help now, or is not that valid now, at least.
Yeah, so that's a great question. Right now, what is happening is all of these companies, OpenAI, Google, Microsoft, uh, uh, do you know, I mean, in business news, NVIDIA is this company, right, that used to make graphics chips. And somewhere along the way, they started realizing that all these deep learning workloads, uh, they could just repurpose those chips to also do a very good job of accelerating deep learning workloads. So NVIDIA stock just went up 26% in one day uh, last week. And I learned it the hard way because I just sold off. I was smart enough to buy some NVIDIA stock, and I figured right now, I mean, there's all this market had gone up. I mean, my NVIDIA stock had really appreciated a lot. So I said, oh, I'm selling it at a great profit. I sold it off. And in one day, it went up by 26%. The reason is because all these AI companies today are investing loads and loads of money into putting together, even though Moore's law has slowed down, all these models are getting trained on increasingly more and more powerful hardware. In Google, it is well known that most of the kind of right now, they've even announced it, that most of the departments kind of, they've been asked to give up their compute hardware that they were using and make it available to this Gemini effort. And it is because so that they're able to train, that Gemini team is able to train an even larger, more capable model. OpenAI got this huge investment from Microsoft, multi-billion-dollar investment. Most of it is going into the hardware, which is being used to train and run these models. So even though Moore's law is no longer kind of that active, the advances in the power of these deep learning models is still being largely driven by the compute. Yeah.
Sir, I have one final question.
Yeah.
Sir, like practically it sounds that cluster analysis should be more accurate than linear regression. But why is it so that linear regression turns out to be more accurate than cluster analysis? So
So,
because in cluster analysis, we have a variety of options to like label data into, but in linear regression, there's only one slope that we can make. So, sir, like, how is it possible that it is more accurate?
it really depends on what problem. So you cannot make a general statement that linear regression will always do a better job than cluster analysis. On specific problems, uh, uh, it will work better on especially, let's say, if you were, if you did not have any labels, if you needed to come up with kind of inherently, let's say, solving that problem, you rely on things like cluster analysis as an unsupervised method to tackle. Uh, so what is happening is in the process of coming up with those clusters, these models are coming up with some representations of those data points. So the power of deep learning networks is coming up from those implicit representations of the data that they are forced to come up with. Just like BERT, so I mentioned that to fill in those blanks, you had to come up with an understanding of the world. So for BERT as a model to fill in those blanks correctly, it has to come up with representations of the world. So these unsupervised or self-supervised methods are forcing these deep learning neural networks to come up with good representations of the world, of the data, which are leading to some of their better performance on many, many different kinds of problems, and also being able to generalize across different problems.